Alright, this is the third and final video of our kind of lesson on modeling here. And again, there is a little bit of writing involved, which I do apologize for. But I want you guys to get these tables all down in your notes. Copy it down, pause the video. And after you do that, we're going to talk about how you can identify from an equation, from a table, what the equation will be. So go ahead and pause this real fast, and we'll go through these. I'm going to try to power through them pretty quickly. Be careful that you copy them down correctly. So I'm assuming you now have these tables down right here. And if they give you a random table of numbers, you could go ahead and graph the table. So you do it like the last video where you just graph the points and see what shape they make, and that would be fine. But with a lot of these tables, there is a shortcut where you don't have to actually make the graph. Okay? When you see a constant table, let's start with this first one here. I'm going to kind of make notes on my graphs right here to talk about them. Constant graphs, the y's should already be the same. If they're already the same when you walk up to the problem, it's constant. It never changes. Linear we've done before. And when you do linear equations, you have to look at how much you're going up or down by and do finite differences, which is the process that I've shown you guys before, where you look at how much you increase or decrease. That's in chapter 6 if you need to look back at it. So that would be, I think it's in like 6-2. I should have looked it up before I started the video here. But it's in section 6.2 or 6.3. You can look back at that and use finite differences. So you would be like, oh, it goes down 4, it goes down 4, it goes down 4. It worked on the first try, so it's degree 1, which is linear. Okay? The same thing is going to be true with quadratic and with cubic. So I'm going to go fast to this and write the numbers on there just to show you guys. This one works on the second try, so it's degree 2. And this one is going to work on the third try. Again, I understand that there's a fair amount of writing in this video here, but it's for the best, just so you can have it copied down here. We would do the finite difference process, and it's going to work on the third try here, so it's degree 3. So linear, quadratic, cubic are all just finite differences, like we've learned before. When you have a table that is exponential, you are going to be multiplying by the same number right here. And it's not easy to see what you multiply by to get from 81 to 54. So same way with these tables, you can do bottom minus top. You can do to figure out if there's a pattern here, bottom divided by top. So if I do 54 divided by 81, that's 2/3. I do this number divided by this one. And if you check, that pattern does hold. It's times 2/3, times 2/3, times 2 over 3, times 2 over 3. So if you multiply by the same number, that is an exponential pattern. For my next table here, logs are a little bit weird. They're not going to come up a whole lot in tables, but the only one, for every other kind of equation, the x's have to be doing the same thing. They have to be increasing by the same amount. If x's were all over the place, you would just graph this. But with logs, they're the only graph where that isn't the case. When you have a log graph, the x's actually get multiplied by the same thing each time. That's the easiest way, anyway, to pick out an obvious log graph. The y's are consistent. The x's are being multiplied. It's like a reversed or flipped version of an exponential. So that won't come up a whole lot, but I'd like you guys to have at least seen it. You multiply the x's, the y's are steady. 2 more on here. Absolute value. You're going to look at the y's, and when you do finite differences, it goes down 2. It goes down 2. Then it switches and it goes up 2, up 2. It's the same number, but it switched directions. That makes it absolute value. So if you have negatives and positives of the same number like that, and it goes from one to the other, that's an absolute value graph. For my last one here, periodic's a little weird, and it's hard to describe, and it's probably not going to come up on a test or anything like that, but just so we've covered it, you guys are at least familiar with the concept here, it rises and falls in patterns. So this one went down and up, but that was it, just one time. You can maybe argue it could have been periodic, but there's not enough points. This is down and up, it's absolute value. This one goes 7, 8, 9, then back down 8, 7, then back up 8, 9. If it kept going, it would go 8, 7, 8, 9. It just keeps going up and down and up and down and up and down in the same pattern like that. So if it keeps rising and falling, rise or fall in a pattern like that or a wave, that means that the table is going to be periodic. That one is a little harder to come up with examples for. It's not going to happen as much. You need more data for it, but that's the idea. With all of these, though, guys, if you do not see the pattern from the table, you can always graph these points and look for the shape of the graph. That will also get you the correct answer.